Now we'll do problems and probability. First one, what is the chance that a leap year selected at random will contain 53 solar days? What is the chance that a leap year selected at random will contain 53 solar days? See here, leap year. Leap year means we get 52 complete weeks plus 2 days extra. 2 days extra. So in leap year we have totally 52 complete weeks. So in that 52 weeks we will get 52 Saturdays. We require here 53 Saturdays. So those 2 days extra may be here a combination of Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, or maybe Friday, Saturday, and finally Saturday, Sunday. So leap year has 52 complete weeks and 2 days extra. So in that 52 complete weeks we'll get 52 Saturdays, but we require 53 Saturdays. 53 means 2 days extra may be any one of these combination. Sunday, Monday, Tuesday, like this. But here we require only Saturdays. Saturday means where we get Saturday combination here, Saturday, Sunday, Friday, Saturday. So in this one we get a Saturday combination. So number of variable cases for 53 Saturdays are 2. So what about total number of possible cases here? 7. So I can write required probability. Number of variable cases for 53 Saturdays are only 2. By total number of possible cases are 7. So here the 2 by 7 is the correct answer. That is option A is correct for first question. Now we'll come to that second question. A fair die is tossed 2 times. The probability that a second toss result in a value that is higher than the first toss. A fair die is tossed 2 times. The probability that second toss result in a value that is higher than first toss. So here second toss. So for see here, let A be the event that getting second toss result in a value that is higher than the first toss. Then the favorable cases will be like this: 1 2, 1 3, 1 4, 1 5, 1 6. Next we'll get 2 3, 2 4, 2 5, 2 6. Similarly 3 4, 3 5, 3 6. Next 4 5, 4 6. Next 5 6. So in all these cases the second toss result in a value that is higher than the first toss. Here 1 2, 2 is greater than 1, 1 3, 3 is greater than 1, 1 4, 4 is greater than 1, and so on. Here 5 6, 6 is greater than 5. So you count all these variable outcomes, you will get 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So total number of variable cases for getting second toss in a value that is higher than the first toss, or 15 number of variable cases are there. What about total number of possible cases here? Die is tossed 2 times. 2 times means 6 square, that is 36. Therefore required probability is equal to number of variable cases by total number of possible cases. Total number of possible cases are 6 square because die is tossed 2 times. So you get 15 by 36. That is which is equivalent to 5 by 12, which is equivalent to 5 by 12. So answer for the second question is C, 5 by 12. Now we'll go to that third question. The box 1 contains chips numbered 3, 6, 9, 12 and 15. Box 2 contains chips numbered 6, 11, 16, 21 and 26. 2 chips, one from each box, are drawn at random. The numbers written on these chips are multiplied. The probability for the product to be an even number. So what I am saying here, 2 chips, one from each box, are drawn at random. The numbers written on these chips are multiplied, the probability for the product to be an even number is, should get product to be even number. So you have to draw one chip from box 1, one chip from box 2, but multiplying both together, but that product should be even number. So in this case, the product should be even number means, see, when will you get even number? See here, box 1 contains chips, box 1 contains chips of 3, 6, 9, 12 and 15, and box 2 contains chips numbered 6, 11, 16, 21 and 26. 26. Now we have to draw one from box 1, one from box 2. So here, what is the required probability? Let us say P of A is the required probability. P of A is equal to, I said, N of A by N of S. Number of variable cases by total number of possible cases. What about total number of possible cases here? Taking one chip from box 1. Here, how many chips are there? Here are 1, 2, 3, 4, 5. So 1 from box 1 means 5C1 into 1 from box 2. Box 2 also here 5 chips, 5C1. Selecting 1 from box 1 is, it can be done in 5C1 ways, into selecting 1 from box 2 out of 5, that can be done in 5C1. So 5C1 into 5C1. What about numerator part here? That is the required thing here. So you should get the product should be even number. When will get product should be even number? See here, box 1 contains both even numbers as well as odd numbers. Box 2 also contains both even numbers as well as odd numbers. So product to be even number, if and only if, see here, we know that even into even into odd number, even, odd into even, also even number. So even into even, even into odd, even, odd into even, also even. Now, see here, from box 1, see, what about even numbers here? How many even numbers are there here? 6, 12. So 2 even numbers are there. So 2 even numbers. So I said even into even. So taking even from box 1, 2. Taking even from box 1. So 6, 12, only 2 even numbers, into, what about even from box 2? Even from box 2. So even from box 2 means we will get here 6, 16 and 26. 3 even numbers are there. So 2 into 3. That is one combination. Plus, next taking even from box 1 and odd from box 2. So even means 2 numbers are even here, 6, 12, into odd numbers. What about odd numbers from box 2? We get odd numbers means we get here 11, 21. Only 2 numbers are odd. So 2 into 2 will get 2. Plus, next combination, odd into even. Taking odd numbers from box 1. Odd numbers are 3, 6 and 15. So 3 numbers are there, are odd numbers. 3 into even from box 2. Even from box 2 means we'll get 6, 16 and 26. 3 even. So multiply with 3. So we'll get here 9, 3 into 3, 9. So we'll get total number of variable cases, that the product to be even number are 19. So we will replace with 19. So 19 by, I can write 5 into 5 is 25. So the answer is option D. Next problem on probability. One card is drawn from a regular deck of 52 cards. What is the probability of a card being either a red or a king? Card being either a red or king. See here, red cards. How many red cards are there? How many king cards are there? See, totally we have 26 red cards. So red or king means let A be the event of drawing a red card and B be the event of drawing king card. So red or king means what find out P of A union B. R means we'll get union and means intersection. So using the addition theorem of probability, I can write P of A plus P of B minus P of A intersection B. So probability of drawing a red card. So 26 red cards are there. So out of 26 red cards, we will draw only one card. That can be done in 26C1 ways. 26C1 by 52C1 plus probability of drawing a king card. So totally there will be 4 king cards. Out of 4 king cards, you draw only 1 king card. That can be done in 4c1 ways by 52c1 minus the probability of drawing a red king card. How many red king cards are there? So in red cards, there are totally 2 king cards are there. So 2c1 by 52c1. The combination part. Red king cards are 2. So we'll get here 26c1, 26, 4, 26 plus 4, 30, 30 minus 2, 28. So 28 by 52 will get. This is the answer for the fourth question. 28 by 52. Now, see that fifth question. In drawing one card from a deck of 52 cards, find the probability that a single draw will be either a face card or a spade card. So here let A be the event of getting a face card and B be the event of getting spade card. Let us suppose that A be the event of getting a face card, B be the event of getting a spade card. Now we require a spade, we require either a face or spade card. R means we will get union. P of A union B is equal to IN using addition theorem of probability. I can write P of A plus P of B minus P of A intersection B. So here P of A, probably drawing a face card. There are totally 12 face cards are there. So out of 12, let draw only one. So that can be done in 12c1 ways. 12c1 by 52c1 plus probability of the drawing a spade card. There are totally 13 spade cards are there. 13c1 by 52c1 minus probability of drawing face spade card. See here in spades, how many face cards are there? So in spades, so we'll get here in 2 spades. What about face cards? Means I said J, K, Q are face cards. J, K, Q are face cards. So in spades, you will get 3 face cards are there here. 3 face cards. So that I can write minus 3c1 by 52c1. So in each suit, in spades, clubs, hearts, diamonds, in each suit we'll have 3 face cards. 3 face cards. So subtract that part here, 3c1 by 52c1. So you'll get here 12 plus 13, 25 minus 3, 22. 22 by 52 is the answer. These are face cards. This is the answer for the fifth question. Now see that sixth question. A bag contains 4 green, 6 black and 7 white balls. A ball is drawn at random. What is the probability that it is either a green or a black ball? Either a green or black ball. Let A be the event of getting green ball. Let us suppose that B be the event of getting green or black, we require black ball. So the required probability is green or black means we will get union. P of A union B is equal to P of A plus P of B minus P of A intersection B. So what is the probability of getting a green ball? So how many green are there? 4. So out of 4, let's draw 1. So 4c1 by, so total number of balls are 6 plus 4, 10, 10 plus 7, 17. So 17c1 will get plus probability of drawing a black ball. So probability of drawing a black ball. How many black are there? 6. So 6c1 by 17c1 minus, what about this part here, A intersection B? Is there is any ball which is green and black both together? No. So green, that part is here 0 because here A and B are, I can say that mutually exclusive. If A and B, I said if A and B are mutually exclusive, that P of A intersection B part is 0. So what are mutually exclusive? I said both 2 events are said to be mutually exclusive. Both cannot happen simultaneously. Both cannot happen simultaneously. Here getting green, or can you get a green and black ball together? No, that is not possible. So that here getting green and black ball both together, that is both are here mutually exclusive. So that part P of A intersection B value 0. So we get finally 6 plus 4, 10, 10 by 17. So this is the answer for the sixth question. Here in this one, the important observation is, since here A and B are mutually exclusive, this part P of A intersection B value will become 0. Now come to that seventh question. The probability that a given positive integer lying between 1 and 100 is not divisible by 2 or 3 or 5. Is not divisible by 2 or 3 or 5. So now first we will say not divisible by 2 or 3 or 5 means, let's see here, let A be the event of that is a number divisible by 2. Let us consider. Let A be the event that number divisible by 2. B be the event that number divisible by 3. Let C be the event that number divisible by 5. Now here what is the required probability not divisible by 2 or 3 or 5? Means I can write here P of A bar intersection B bar intersection C bar, that is equal to, I can write P of 1 minus P of A union B union C. Using properties, I can write P of A bar intersection B bar intersection C bar. Here A bar means that is the not happening of event A, B bar not happening of event B, C bar not happening of event C. So not divisible by 2 or 3 or 5 is equal to 1 minus probability of divisible by 2 or 3 or 5. 1 minus probability of a number divisible by 2 or 3 or 5. So here that is equal to, here using that addition theorem of probability for 3 events, I can write P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of C intersection A plus P of A intersection B intersection C. So 1 minus P of A, where represents here a probability that a number divisible by 2. See, 1 to 100 both inclusive. How many numbers are there which are divisible by 2? Divisible by 2 means there exists 50 numbers divisible by 2. 1 to 100 both inclusive. So 50 by 100 plus number divisible by 3. So 1 to 100 both inclusive. There are totally 33 numbers are there divisible by 3. So we will get 33 by 100. Number divisible by 5, 20 are there, 20 by 100 minus number which is divisible by 2 and 3 both. Number which is divisible by 2 and 3 both means, see how can you find number which is divisible by 2 and 3 both, means that number should be divisible by LCM of 2 and 3. LCM of 2 and 3. So LCM of 2 and 3 is 6. So the number of numbers divisible by 2 and 3 between 1 to 100 both inclusive is equal to number of numbers which are divisible by LCM of 2 and 3, that is 6. So how many numbers are there between 1 to 100 both inclusive divisible by 6? Divisible by 6 means there exist 16 numbers. 16 by 100 minus B intersection C means number divisible by 3 and 5 together is divisible by LCM of 3 and 5. LCM of 3 and 5 means that is a 15. So number of numbers divisible by 15 from 1 to 100 both inclusive. So both inclusive means we will get 6 numbers minus C intersection A means number of numbers divisible by 2 and 5 both. 2 and 5 both means LCM of 2 and 5 is 10. So number of numbers divisible by 10 from 1 to 100 both inclusive will be 10. 10 by 100 plus A intersection B intersection C means numbers which are divisible by 2 or 3 or 5. Sorry, 2 and 3 and 5. 2 and 3 and 5 means, so there is a number of number divisible by LCM of 2 and 3 and 5. So LCM of 2 and 3 and 5 is you'll get 30. LCM of 2 and 3 and 5 is 30. So number of numbers divisible by 30 from 1 to 100 both inclusive will be 3. 3 by 100. So we'll get this one as a 1 minus, we'll get a 74 by 100. Simplify this one, we'll get 74 by 100. That is equal to 26 by 100 is the final answer. We'll get 26 by 100. So this is the answer for that seventh question, 26 by 100. This is a problem on conditional probability. That the chance of student passing an exam is 20%. The chance of a student passing the exam and getting above 90% marks in it is 5%. Given that a student passes the examination, the probability that the student gets above 90% marks is, the chance of a student passing an exam is 20%. So the chance of a student passing the exam and getting above 90%, above 90% marks in it is 5%. Given that a student passes the examination, the probability that the student gets above 90% marks is, see here, let us consider here A. A is the event of student passes the exam. Student passes the exam. And B is the event student passes the exam and getting above 90%. Student passing the exam and getting above 90%. I'm getting above 90%. Student getting above 90%, not student getting above 90%. When you get above 90%, means then the student definitely has to pass the exam, then only you get above 90%. So it is given that P of A is given as 20%. 20% means 20 by 100, we will get 1 by 5. And P of B, student getting above 90%. So above 90% is 5% given. So 5 by 100, so we get 1 by 20. 1 by 20. Sorry, this one is not P of B. It is given that the student passes the examination and getting above 90%. Means it is given that P of A intersection B part. P of A intersection B part is 5%. This is 5 by 100, 1 by 20. Because student getting above 90% means then definitely student has to pass the exam. So P of A intersection B is equal to 5%, that is a 5 by 100, 1 by 20. What is the required thing here? Given that student passes the examination. See here, that is a conditional event. Student passes the exam means here, what is the passing the exam here? Write A in denominator. And getting above 90%, B in numerator. So P of B given A. See, P of B given A means what does it refers here? P of B given A means student passes the examination and getting above 90%. Student passes the examination means first you write A in denominator. I said P of B given A means probability of happening of the event B under the condition that the event A is already happened. A is already happened. After passing the exam only you will get above 90%. So that is using that conditional probability definition. I can write P of A intersection B by P of A. So P of A intersection B part is 1 by 20. 1 by 20 by P of A is 1 by 5. So we'll get 5 by 20, 1 by 4 will get. 5 by 20, 1 by 4. That is option B is correct. So given that student passes the examination, the probability that student gets above 90%, passes the examination and gets above 90%, that is the P of B given A. So now see that ninth question. A coin is tossed 3 times. It is known that out of the 3 tosses, one is head. one is head. The probability that the other two tosses also being heads is, so a coin is tossed three times. So three times, what is the corresponding sample space of that coin here? It will be like this: HTH, THH, TTH, THT, HTT, HTT, and finally TTT. This is a sample space of coin tossed three times. So here it is known that out of three tosses, one is head. The probability that the other two tosses also being heads. So this is also a conditional, using conditional event. I can write here P of one is head. What about other two also heads? Here one is head. Writing in denominator because that event is happening first. Other two tosses being heads, other two also heads, other two being heads. So one is head is happening first, so I'm writing that event in denominator because P of, let us say this is a A given B. This event is happening first. In P of A given B, the event B is happening first. After happening of the event B, the event A is happening. So P of A given B means one is head and other two being heads. So using the definition of conditional probability, I can write P of A intersection B by P of B. What is the P of A intersection B here? That is a combination of both the events here. One is head, other two being heads. What is the intersection part here? So here other two being heads, one is head, other two being heads. Here that means all three heads will get. All three heads means we'll get only one combination. So we'll get here 1 by 8 by. So what is the probability of getting one is head? One is head means there are how many possibilities are there? One is head here. One is head. 1, 2, 3, 4, 5, 6, 7. So one in all these events, one is head. So we get 7 by 8. So we get finally 1 by 7 is the answer. So that is the probability that other two also being heads using that definition of conditional probability. And now we can do the same problem without applying that conditional probability definition also. As a method 2, or we can do like this also. So first I will define one sample space for one is head. So HHH, HHT, HTH, THH, TTH, THT, HTT. This is the sample space. I'm redefining sample space. That is S1 here. This is a sample space for one is head. Sample space for one is head. Sample space for one is head. So I'm removing that all tails. If you remove that all tails, you will get sample space for one is head. Now, what is the probability that the other two tosses also being heads? So the required probability is equal to other two also being heads means all three heads. All three heads means there is only one variable case for all three heads. So 1 by, what about here for one is head, sample space contains how many sample points? Here is 7 sample points. So the required probability is 1 by 7. So we can apply conditional probability definition, or we can do like this also. So both gives same answer 1 by 7. That is the correct answer. So that is option A is correct. Next problem, probability. An examination consists of two papers, paper 1 and paper 2. The probability of failing in paper 1 is 0.3 and that in paper 2 is 0.2. Given that a student has failed in paper 2, the probability of failing in paper 1 is 0.6. The probability of a student failing in both the papers is. So this is application of multiplication theorem of probability. Now, see here, it is given that an examination consists of two papers, paper 1, paper 2. The probability of failing in paper 1, let us say P of 1, is given as 0.3, and that in paper 2, P of 2, probability of failing in paper 2, 0.2. Given that a student has failed in paper 2, the probability of failing in paper 1. See here, failed in paper 2, write 2 in denominator. Failing in paper 1, there is a conditional probability is given, that is 0.6. Failed in paper 2, so here that event 2 is happening first. Failing in paper 2 is happening first. Failing in paper 1 is given as 0.6. The probability of a student failing in both the papers. So failing in both the papers means you have to find out P of 1 intersection 2. Failing in both the papers. So I can write this one as P of 2 into P of 1 by 2. So using that multiplication theorem of probability. What is multiplication theorem of probability? I said P of A intersection B is equal to, I can write P of A into P of B given A, or which is same as P of B into P of A given B. Applying that multiplication theorem of probability. So P of A intersection B is equal to probability of simultaneous occurrence of any two events is equal to unconditional probability of any one event multiplied with the conditional probability of other event. That is the multiplication theorem of probability. So P of 2 is 0.2 into, we get P of 1 by 2 is 0.6. So we get 0.12. So option C is correct. So probability of student failing in both the papers by applying that multiplication theorem of probability. See, the final answer will be 0.12. Now come to that question number 11. From a pack of regular playing cards, two cards are drawn at random. What is the probability that both cards will be kings if the first card is not replaced? If the first card is not replaced. From a pack of regular playing cards, two cards are drawn at random. What is the probability that both cards will be kings if first card is not replaced? See here, let K1 be the event of drawing first king card, K2 be the event of drawing second king card. Both, that is K1 intersection K2 is equal to P of K1 into P of K2 by K1. Using multiplication theorem of probability, I can write P of K1 intersection K2 is equal to P of K1 into P of K2 given K1. So probability of drawing first king card. So how many king cards are there in that pack of cards? Totally 4 king cards. So out of 4 I draw only one. That is a 4C1 by 52C1. 4 by 52 will get. Into here, into here it is given that the card is not replaced. That card is not replaced. So without replacing that first king card, we are going for drawing second king card. So here P of K2 given K1 nothing but probability of drawing second king card under the condition that first king card is not replaced. So if first king card is not replaced, what about here? See, what about total number of cards? Remaining king cards will be 3 only. Total number of cards 51. We are not replacing that first king card, so remaining king cards will be only 3. So out of 3 king cards, we will draw 3 by 51. Total cards will be 51. So multiply this one, simplify, we get 1 by 221. 1 by 221. We can go for this formula, directly you can do here. Probability of drawing, what is the required probability, I can write like this. Probability of drawing first king card is 4 by 51, 4 by 52 into without replacement. Without replacement means there are only 3 king cards are there. There will be only remaining 3 by 51. So that formula indicates this one only, 4 by 51 into 4 by 52 into 3 by 51. So we'll get finally option D, 1 by 221. That is the answer. Now we'll come to that question number 12. A class has 10 boys and 5 girls. 3 students are selected at random, one after another. Find the probability that first question is first two are boys and third is a girl. First two are boys and third is a girl. Means you can arrange like this: boy, boy, girl. First two are boys means I can give positions like this: 1, 2, 3. First two positions boys and third position girl. So taking probability intersection. So using that multiplication theorem of probability, I can write P of B1 into P of B2 given B1 into P of G3 given B1 intersection, that multiplication theorem of probability for 3 events. Here 1, 2, 3 represents corresponding positions here. First position boy, second position boy, third position girl. So probability of drawing a boy here, see here, selecting a boy. How many boys are there here? Totally 10 boys are there. Out of 10 boys, I select only one boy. So 10 by, total number of students are 10 plus 5, 15. 10 by 15 into, next selecting a boy under the condition that first boy is, first selected student is boy. So already one boy is gone here. So remaining boys are 9. 9 by 14 will get. Into selecting a girl under the condition that first two selections are boys. So selecting a girl means here how many girls are there? 5 girls are there. 5 by, so already 2 boys are gone. So remaining students will be only 13. So simplify this one, you will get answer. 10 by 15 into 9 by 14 into 5 by 13. That is the answer for the first question. Now if you see that second question, first and third of same gender and the second is of opposite gender. So first and third of same gender means I can write this here first and third. First and third I can fill with boys, and second is of opposite gender means I can insert a girl in between two boys, or I can go for another combination. First and third I can take girls, girl, in between two girls I can insert boy. You can go for this combination or this combination. So corresponding positions 1, 2, 3. Probability P of first position intersection, second position boy, third position girl. So either this or this means you can get these two are mutually exclusive events. I said if A and B are mutually exclusive, what is the P of A union B? P of A union B is equal to P of A plus P of B. So I can write here that is equal to here what is the probability of this one here? Probability of selecting a boy here. Selecting a boy means you will get a 10 here. 10 by total number of students are 15 into next applying same this formula here we will get P of G2 by B1. So probability of selecting a girl 5 by 14 into P of B3 by B1 intersection G2. That is selecting a boy here. Already one boy is gone, so 9 by 13 plus this is a part. P of B means this is the part here. P of B R. So P of G1 selecting a girl, so we'll get 5 by 15 into next selecting a boy. Selecting a boy 10 by 14 only into next selecting a girl. So already one girl is gone, so we'll get 4 by 13. So simplify this one, we'll get answer. That is a selecting that is a probability of first and third of same gender, and second is of opposite gender. Next question: a box has a total of 10 identical sized balls. 7 of these balls are black in color, and the rest 3 are in red. 3 balls are drawn from the box one after another without replacement. The probability that 2 of the balls are black and 1 is red. See here, total of 7 identical sized balls. Total balls are 10. Out of 10 balls, 7 of these are black in color. 7 black and rest 3 are in red. 3 red. three balls are drawn from the box one after another without replacement, the probability that two of the balls are black and one is red. So two black, we require two black, one red. So we can take like this here, black black, we'll get a combination like this, two black, one red, black black red, or black red black, or we may get red black black. So we'll get three different combinations with two black and one red. So what is the either this one or this one or this one. So R means we'll get see what is the probability of getting first here a black ball. How many black balls are there? 7 black balls are there. So 7 by total number of balls 10 into, this is a without replacement. So without replacement means after one ball drawn here, one black ball drawn, remaining black balls will be only 6. So 6 by 9 into, next red are 3 by 8 without replacement, plus R will get this combination. For this combination, first we have to draw black ball. So that is a black ball means 7 by 10. Next red ball 3 by 9. Next black ball, so we get 6 by 8 plus first red 3 by 10 into next black 7 by 9 into next again black 6 by 8. All these three events are mutually exclusive. That's why I'm adding all these three. So getting BBR, BRB, RBB, all these three events are mutually exclusive. I said if A and B are mutually exclusive, P of A and B is equal to P of A plus P of B for two events. For three events, P of A union B union C is equal to P of A plus P of B plus P of C. So simplify this one. We'll get simplify this one. Finally, it will give 21 by 40. 21 by 40. Multiply and add all these things and simplify. We'll get finally it will give 21 by 40. So this is the answer for the 13th question. Now we can do 13th question in another way also. So the probability of getting a probability that two of the balls are black, one is red. Two black, one is red means we can go for two black. So out of 7 black, so taking two black, so that can be done in 7C2 ways. Two black, one red. So 3 balls are red. So out of 3 we will draw only one. So 7C2 by 3C1 by total number of balls we are drawing 3 balls. So 10C3. So simplify this one again, it will give 21 by 40. So both are correct way. You can do like this or like that. Both are correct. Why I am doing like this here, 7C2 into 3C1 by 10C3. See, all these here drawing black ball, drawing red ball are independent. I said one condition, if P of A intersection B is equal to P of A into P of B for two events. For three events we can take like this. For three events, consider three events. P of A intersection B intersection C is equal to P of A into P of B into P of C for three events where ABC are independent. ABC are independent. Here we require only 2 is enough. Said A and B together is equal to 1 by 1. A and B together is equal to 1 by 1. That is only for independent events. If A and B are independent, then I consider P of A intersection B is equal to P of A into P of B. That is A and B together is equal to 1 by 1. So now, so what is here? See, this is 1 by 1 here. 1 by 1 is equal to A and B together. These are together. So since here events are independent here, drawing black ball, drawing red ball are independent. So I can apply here A and B together. Together means here uh, drawing two black balls and one red ball together, drawing two black balls and one red ball together is equal to 1 by 1. 1 by 1 means this one. So drawing first black ball, next black, and next red, or black, red, black, or red, black, black. So whatever may be the method, both the methods are correct. So both the methods will give same answer, 21 by 40. So this is the answer for the 13th question. Next we will go for 14th question. If one bucket contains 8 red balls and 2 black balls, 8 red balls and 2 black balls, another bucket contains 7 red and 3 black balls, the probability of having at least one red ball from drawings of one ball from each of the two buckets. We require at least one red ball from drawings of one ball from each of the two buckets. Here one bucket contains 8 red and 2 black. Another bucket contains 7 red and 3 black. We require at least one red. At least one red means from first bucket we can choose red. From second bucket black. Or you may go for black red. Or both red. At least one red means one or more than one. So you can go for these three combinations. Red from first bucket, black ball from second bucket, or black from first bucket, red from second bucket, or both red from first bucket, red from second bucket. So this can be done in like this here. First red from first bucket. What is the probability of drawing red from first bucket? So 8 by 10 into, next what is the probability of drawing black from second bucket? 3 by 10. Why multiplying here? Why multiplying means drawing red ball and drawing red ball from first bucket and drawing black ball from second bucket, both are independent. I said if A and B are independent, P of A intersection B is equal to P of A into P of B. So again R means we will get plus R. What about black from first bucket? So we will get 2 by 10. Next red from second bucket, 7 by 10, plus next red from first and red from second. Red from first means 8 by 10. Next red from second, 7 by 10. So that is the required probability. So we'll get here 24 by 100, 14 by 100, 56 by 100. So 56, 60, 70, 18, we'll get totally 94 by 100. 94 by 100 is the answer for this question. Now come to this 15th one. 15th question. A fair coin is tossed 3 times. A fair coin is tossed 3 times in succession. If the first toss produces head, then the probability of getting exactly 2 heads in 3 tosses. 2 heads in 3 tosses. This is a application of the conditional probability. Probability of getting exactly 2 heads in 3 tosses. What about first toss must be head? So probability of first toss head and getting exactly 2 heads in 3 tosses. Exactly 2 heads in exactly 2 heads in 3 tosses. So that will be, this is a A event, B event. Here the event B is happening first. First toss head, exactly 2 heads in 3 tosses. So using that conditional probability definition, I can write P of A intersection B by P of B. So what is the P of A intersection B? Getting exactly 2 heads in 3 tosses and first toss head. What is that probability here? Let us consider, see what is the sample space in tossing 3 coins. We will get HHH, HHT, THH, HTH, TTH, THT, HTT and TTT. This is the sample space for 3 coins. 3 times. A coin is tossed 3 times or for 3 coins, both are same. So P of A intersection B, probability of that is getting exactly 2 heads in 3 tosses, and first toss must be head. So what is the first toss must be head here, and getting exactly 3 heads in 3 tosses. First toss head and exactly 2 heads. So 1, 2, exactly 2 heads. Means you cannot take this one. First toss head and exactly 2 heads. First toss head and exactly 2 heads. Here first toss head and exactly 2 heads. No. Here only 1 head. First toss head exactly 2 heads. First toss head exactly 2 heads. So this is the corresponding probability here. Number of variable cases are only 2. So 2 by 8. 2 by 8. Now what is the probability of B here? B nothing but probability of getting first toss head. So how many first toss head variable cases are there here? First toss head means this is also first toss head. First toss head. First toss head and first toss head. So 4 variable cases are there. 4 by 8. So 2 by 8 by 4 by 8, that is equal to, you get a 1 by 2. So this is the probability. So probability of getting exactly 2 heads under the condition that first toss head is 1 by 2. So this is one way. Now we can do this problem in another way also. Or I will define sample space for first toss head. Let S1 be the sample space, that the first toss head. What is the sample space for first toss head? We will get only 4 elements in that sample space. This is the sample space for first toss head. First toss head. Now getting exactly 2 heads in 3 tosses. What is the required probability here? Required probability. First toss head getting exactly 2 heads in 3 tosses. So exactly 2 heads means you will get here in this combination and in this combination. Exactly 2 heads in 3 tosses. So favorable cases are 2. Total number of possible cases are 4. So 2 by 4 is equal to 1 by 2. 2 by 4 is equal to 1 by 2. Or we can do the same problem in another way. That is a method 3. This is a method 1, method 2. Now I am going for method 3. The method 3 is see here first toss is head. This is head. Probability of getting exactly 2 heads in 3 tosses. So here we will get T or H, H or T. That is a fixed. First toss head is fixed. Now getting exactly 2 heads in 3 tosses means what about possibilities for remaining here? We may get either TH or HT. So what is the probability of getting here? See here TH or HT. Probability of getting these events TH or HT. So for getting TH, what is the probability of getting tail is 1 by 2 into these 2 events are independent, that's why I am multiplying, into probability of getting head also 1 by 2. Or means we will get plus because these 2 events are mutually exclusive. So again probability of getting head 1 by 2, probability of getting tail 1 by 2. So we will get 1 by 4 plus 1 by 4, that is equal to 1 by 2. So this is method 3. This is the method 2, this is method 1. So we can do this problem in 3 ways. Can do this problem in 3 ways. So whatever may be the method should get the same answer. So should get answer 1 by 2. Problem. The figure shown the semantic of a production process with the machines ABC. An input job needs to be pre-processed either by A or B before it is fed to C, from which the final finished product comes out. The probabilities of failure of the machines are given as P of A, P of B, as P of A, failure of machine A, 0.15, failure of mission B 0.05, failure of mission C 0.1. Assuming the independence of failures of the machines, the probability that a given job is successfully processed. So, given job is successfully processed means see here, we can do this problem in two ways. Probability that input job processed by C, there is a job to be completed successfully. Job to be completed successfully, a required probability is equal to, I can write P of here machine A or B success and machine C success. Required probability, that is a probability the given job is successfully processed. Processed means it has to come finished product out. It has to come from C. C means here probability that mission A or mission B success, because these two are parallel. So out of these two missions, only one is enough. At least one of A and B, mission A or B success, and mission C success. So again, this one has P of A union B intersection C. A or B success, and definitely see here machine C success is required, otherwise we can't get the finished product. So A or B success and mission C success, that is equal to, using that distributive property, I can write P of A intersection C plus P of B intersection C minus P of A intersection B intersection C. P of A intersection C plus P of B intersection C minus P of A intersection B intersection C. It is given that assuming independence of failures. So independent, here A, B, C are independent. So A, B, C are independent, I write the P of A intersection C as P of A into P of C, P of B into P of C minus P of A into P of B into P of C, since A, B, C are independent. Notice the P of A probability that mission A success. Mission A success. Here the failures are given here. These are failures of A, B, C missions. The corresponding success at A. Success at A is 1 minus 0.15. That will be the corresponding success. So 1 minus 0.15, that will give 0.85 into P of C success. The P of C failure. P of C success is 1 minus 0.1, 0.9 plus P of B success 1 minus 0.05, you get 0.95. P of C success 0.9 minus P of A success 0.85 into P of B success 0.95 into P of C success 0.9. Simplify this one, it will give finally simplify that one, finally it will give 0.89325. 89325. So this is the required property. This is the one way of doing this question 16 and 16th one. There is another method also there, the method 2. So we can apply method 2 also. We can do, or by applying method 2, see here, we can apply method 2 like this. Here, required probability, I can write like this. Required probability is equal to, I can write what is the input job A and B here. So to find that required probability, first we will go for what is the input job? Input job fails at both A and B. Fails at both A and B. Input job fails at both A and B is given by, so For A, failure is 0.15 into, for B, corresponding failure is 0.05. Multiply these two, that will give 0.0075. The input job fails at both A and B. Now, so what about input job? When that input job comes to C here, input job comes to C, means argument input job fed to C, fed to C is equal to 1 minus 0.0075. If we subtract the corresponding failure probability at both A and B, if you subtract the corresponding failure probability at both A and B, then only that input job fed to C. It will come to here, fed to C. 1 minus 0.0075. Simplify this one, that will give 0.9925. The input job fed to C. So now, what is the success at C here? Input job here processed by C. Input job processed by C. That is the required probability. Processed by C. Input job processed by C is given by here 0.9925 into, what is the success at C here? Success at C, failure at C, C is 0.1, success at C is 0.9. So multiply with 0.9, therefore that will be a required probability input job processed by C. So simplify this one, again it will give 0.89325. So input job fails at both A and B is that one. So if we subtract 1 minus that value, that will give input job fed to C. It comes here. So after coming here, input job processed by C is given by here that probability value into corresponding success at C. Success at C is 0.9. So we will get final answer 0.89325. That is the method 2. So you can go for this method 1 or method 2. So both will get the same answer 0.89325. So this is about question number 16. Now coming to question number 17. ABC are aiming to shoot a balloon. A will succeed 4 times out of 5 attempts. So that is a P of A, probability of success by A is given by 4 times out of 5 attempts, means 4 by 5. The chance B to shoot the balloon is 3 out of 4. 3 out of 4 means 3 by 4. And that of C is 2 out of 3, 2 by 3. If the 3 aim the balloon simultaneously, then find the probability that at least 2 of them hit the balloon. At least 2 of them hit the balloon. So at least 2 of them means here the required probability will be like this. At least 2 of them hit the balloon. At least 2 means 2 or more than 3. Sorry, 2 or more than 2. More than 2 means here totally 3 are there. So 2 and 3, that will give at least 2. You can write like this. Required probability P of A intersection B intersection C. I will put bar here. R means plus P of plus so at least 2 means 2 or more than 2. So here B and C hit the balloon, A does not hit the balloon. A bar means that is a complementary event of A. A bar means not hitting the balloon A. Here A and C hit the balloon, B does not hit the balloon. Here A and B hit the balloon, C does not hit the balloon. Here all 3 hit the balloon. So this is the required probability, at least 2 hit the balloon. So here it is given that see here hitting the balloon by ABC are independent. So 3 different persons here. So hitting the balloon by ABC are independent. So I can write this one as P of A bar into P of B into P of C plus P of A into P of B bar into P of C. Since A, B, C are hitting the balloon by ABC are independent. And also again that if A and B are independent, A bar and B independent, B and A bar independent, A bar and B bar also independent. So using those, so I can write P of A bar means 1 minus P of A. 1 minus P of A means 1 minus 4 by 5 into P of B is 3 by 4 into P of C is 2 by 3 plus P of A is 4 by 5 into P of B bar is 1 minus 3 by 4 into P of C. P of C is 2 by 3 plus again P of A 4 by 5 into P of B is 3 by 4 into P of C bar means 1 minus P of C, 1 minus 2 by 3 plus P of A into P of B into P of C, 4 by 5 into 3 by 4 into 2 by 3. Simplify this one, finally it gives 5 by 6. This is the required probability, that is the probability that at least two of them hit the balloon is 5 by 6.